Since the focus is over here, what I can do to construct the reflected ray is consider the virtual ray going through the focus over here. So if you'll just simply lay out your ruler like so, there we go. I'm going to draw a dotted line for the virtual line over here, but the reflected ray will look like this. And probably another good option would be to reflect off the pole, because there we can...
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Okay, so we're going to take a break from kinematics and do something different. And the reason why is because we haven't actually done any physics yet. And so I wanted to do some physics where things are going to work out rather simply, because when we get into the next stage of kinematics, which is Newton's laws and the laws of motion, it's a little more complicated. And so I want to use a simple principle to illustrate this, and we're going to use something called geometric optics. Okay? The geometrical optics is a branch of optics that is accurate for light within a certain region, as long as because we'll learn later that light has a wave-like nature, right? And if the objects that we're interested in interacting with it are on the order of the wavelength, then we have to talk about the wave nature of light. If they're not, though, if the objects are much larger, then we can talk about things in terms of ray optics. And so we can treat light as a ray, which is something that has a direction. Okay, so they're just lines going in a direction. And so one of the first observations on light was the idea of reflection. And so this was originally done by Hero of Alexandria, probably around the 1st century AD. And he considered, why is it that light reflects the way that it does? And so if we consider a flat mirror, and we were to, take a laser pointer, which Hero of Alexandria wouldn't have had at the time, and bounce a ray off of it, we would see that it comes in, hits some point, and will reflect out here somewhere. You kind of see it there. And so Hero was curious why that would be, if he could understand that. And so the first attempt at understanding light was an idea called the principle of least distance. And so if we consider that this black line here is our flat mirror surface, and we consider 2 points, A and B. And we're going to say that the light begins at point A and it ends at point B. So we have an observer here at B, and we have someone emitting light at point A. Let's consider all the possible paths that it could take. Now we know it bounces off of this mirrored surface somehow. But, what's the path? How do we figure out what the path is? So here I've drawn a few different paths. The brown path, which just comes straight down, hits the mirror, and then bounces over to B. And I've measured, using a ruler, what those path lengths are. And so for the first arm, going from A to the mirror, I have a length of 25 centimeters. And from this point up to B, I have a length of 40.5 centimeters. And so I'm just going to add those two numbers up. I get 65.5. Now we'll consider the black line that I've drawn here. And if I measure the path lengths here, I get that it's 29.5 centimeters for the first leg and 29.5 centimeters for the second leg. So I kind of split the difference between the two. When we add that up, we get 59 centimeters. Now I'll consider another ray, which goes from A to this point here on the mirror, and then back up to B. And those path lengths are 35.5 and 26.5, which add to 62 centimeters. And so if we look at these three different possible light paths and notice something about the black path, that it has the minimum value. That's the minimum distance. And so this is kind of the origin of the principle of least distance. And so Hero thought about it. Well, how can we tackle this from a theoretical point of view and make sure that what we're doing is absolutely right? So we need a good principle here. And one principle that you're probably familiar with already is the idea that the shortest distance between 2 points is a straight line. And so what Hero saw was a straight line being the path forward on this. And so let me just observe that the distance from B to this line, the mirror, is 25 centimeters. So if I extend that line out in the other direction, let me go from 25 to 25 below the mirror's surface, which is going to put us down right about here, somewhere there maybe. And now I'm going to connect up this point A with this point that I've drawn down here. Hopefully I've been careful enough. And what we will see is that the distance between these 2 points is the same. So I'll call this H, and this is H. So you can imagine that if I were to take this mirror and fold it over, right, that this line would come right back on top of this black line. And so this virtual point here, as we'll call it, was what was interesting to Hero. Because now I can easily construct, I'm going to call this point here B prime. Now the shortest distance between A and B prime is, of course, a straight line. So I can now construct that straight line, and this will be the point on the mirror where the light reflects from. Now I'm going to just erase the other colored lines here to get them out of the way, and point out the interesting observation about this, or the interesting consequence of this. If I draw a normal to the surface of the mirror at the point where it reflects, so this is a normal line. I guess I should have drawn this just a little bit better and just fix that region up right there. If I draw a normal from this reflective surface that's perpendicular to the surface of the mirror, which I've totally destroyed here. There we go. So the angle here is the same as the angle here. So we'll call this theta I and theta R. And so this normal bisects this point, which means that we now have something we can call the law of reflection, which says that the angle of incidence with respect to the normal is equal to the angle of reflection with respect to the normal. Now, of course, this also means that this angle here and this angle here are the same. That's just a consequence of geometry. But usually the way that we do it is in terms of the normal to the surface. And the normal, of course, makes a right angle with the flat mirror. And so that's the law of reflection. And Hero thought that it was a consequence of what he called the principle of least distance, right? That light is going to travel the shortest possible path that it can to get from point A to point B. Now, as we showed earlier, any other path that we considered reflecting from the surface with rays, which are just straight lines, would be longer than this path here. And so whenever the angle of incidence is equal to the angle of reflection, we find that that is where light will reflect. We'll come to learn later that this is really not least distance, it'll turn out as least time, because light, we'll find, will travel at finite speed, and so we can think of the distance traveled as the time it took to travel it, and we can think of those two things synonymously. But when we consider transmitting through optical materials like glass, we'll discover the law of refraction, and we'll be forced to abandon least distance and embrace least time. And if you take your studies further, and you get into much deeper physics than we'll learn, this is really just the principle of least action. But that's way beyond what we can talk about here. Okay, so law of reflection. The angle of incidence equals the angle of reflection. Talk a little bit about reflections from flat mirrors. And so consider this surface here to be our mirror, and the surface here to be, this line with the arrow on top, to be like a person. We can think of this as the head and this as the feet. I'm not going to attempt to draw a little man because it probably wouldn't look very realistic. And so what do we see when I look in the mirror and I see my head? We're going to apply the law of reflection, which you'll recall is that the incident angle of the ray is equal to the reflected angle of the ray. But that's with respect to a normal to this surface. Now, since it's a flat mirror, that kind of makes it easy. So the first one I'm going to consider is a ray going straight across. Okay? So if I consider a light ray coming from my eye, and then it's going to bounce straight back because it's incident, it's parallel to a normal to this surface, which means that when it reflects back, it's just going to come back. So that's saying that the angle of incidence is 0, so the angle of reflection is 0. Now, what about when I see my feet? Well, that means that a ray of light had to come from my foot to the mirror, bouncing off and going to my head, or my eye. So what I'm going to do here is I'm going to imagine a ray coming from my foot, and I may have drawn that a little too steep. I think I have. Let me just try that one more time. It's not the easiest thing to do, these lines. Okay, so there's the incident ray. Now I need to construct a normal to that. So I just let a perpendicular line from this mirror surface come out. So this angle here, the exiting ray, needs to follow the same angle. So I'll just kind of guess it from there. And then draw that line. So there is the ray that came from my feet, had just the right angle of incidence to reflect up to my eye so that I see my feet in the mirror. Now, let's extend this idea, because when we look at a mirror, we kind of think that we see someone on the other side that looks a lot like us, right? So what does that mean exactly? How does that work? I can imagine these rays, when I see a ray coming from here, right, and I see a ray coming from here, I can imagine kind of extending these rays into the background here, like this, and then this ray would extend, oops, get the angle right here, something like this. Now you recall from before, when we constructed this virtual point, as I called it, we took a point here, and we imagined the same distance that we have from here to here, going from here to here, let's say, right? And we can do the same thing with our feet. We can take this point here and imagine that it is, whatever this distance is, go this distance into the mirror, and that puts us here. So our head would be up here, and our feet would be down here. And, well, I guess that was not the best place to draw it. It should have been more like this. There we are. I know the distances don't look exactly right, but that's because of my, poor drawing skills up here. So we see the object right side up, so my head looks like it's in the right place. My feet look like they're in the right place, below my head. And so it appears that there's this image from behind the mirror, and these rays, which I see coming in, seem to be coming from these points, like this. So we can consider a variety of flat mirror problems using this idea. I mean, instead of using things that have height, we're going to just consider points. So let's consider the following. If I have a mirror whose edge is here, and it has another edge here, I'm going to put some people. Call this person A, I'm going to call this person B, I'm going to call this person C, and I'm going to call this person over here D. And what I want to know is who can see who in the mirror. Right? So imagine you're sitting here, who can you see in the mirror? How do we figure that out? Well, all we have to do is construct these images. And the way that we construct an image is, let me just create an artificial extension of this mirror. Right? There's no mirror there, that's just a dotted line to let us know where our surface is. And construct a parallel line from here to here. Now whatever that distance is, right, when we measure a parallel from here, so here I get 13 centimeters. So I'm going to go from that same point up 13 centimeters. This will be where my image appears to be. Call that A prime. And we can do the same thing with B, which we'll call B prime, and with C. Okay, so just before the camera cut out and I changed the batteries, I was drawing these virtual images, which are the same distance. So if we draw a normal to this surface, the image is the same distance behind as the real object is in front. So pretty easy to construct. And so what I've done is I've laid out these 4 dots, which we'll call students, A, B, C, and D. And now we're going to ask the question, who can see whom? Now, can A see himself? Well, the way we find out is we construct a ray going from A prime to A. And as you can see here, this does not pass through the mirror, so A cannot see himself. Can A see B? Well, if A sees B in the mirror, he'll see we need to construct a ray coming from B's image, B prime, and going to A. It looks like it can just make it. Just at the edge there. Can A see C? Well, we do the same thing. We need a longer ruler this time. We construct a ray from C prime to A. And so A can see C. And you can probably tell that A will be able to see D as well. Because when I construct a ray going from D's image to A, the line passes through the plane of the mirror. We can then ask, well, who can B prime see? Or who can B see? We can then ask, who can B see? Well, B, it looks like He can see A, but let's just see. Well, if A can see B, then B can see A. So my drawing is not the greatest, which is why this appears to miss. But we'll just let that come over just a bit. B can also see himself, and B can see C, and it looks clear that B can see D. C can see A. We don't need to draw all of these lines, just consider the line going from the image to the point. Looks like C cannot see D, however. It's very close, and I would say no, that's a miss. D obviously can't see himself, but D shouldn't be able to see C either. So if we construct a line from D to C, yeah, D cannot see C. So we have in the final summation here that A can see B, C, and D. B can see A himself, can see C, and what did we rule on B, C, and D? Yeah, it looks like you can see D and D. C can see A, B, C, and I think not on D. So A, B, and C. And then D can see A, B, I think C. Oops. No, we already decided that he couldn't. D can only see A and B. So the only person here that can see everybody is B, which probably makes sense intuitively, but this is how you figure these problems out for flat mirrors. And next we'll consider parabolic mirrors and spherical mirrors. Parabolic and spherical mirrors. So you are probably familiar with parabolas from algebra, and you probably remember that one of the geometrical qualities of a parabola are that there's a special point called the focus of the parabola and a special line called the directrix of the parabola. And that the distance, if we pick a point, we measure the distance from the vertex of the parabola to the focus, it's the same as the distance of the vertex from the directrix. And similarly, any line we draw, any horizontal line, which is a perpendicular line to the directrix, just happens that we oriented our parabola like this. This distance L to the surface of the parabola is the same as the distance from that point to the focus of the parabola. So as you go out, farther, of course, this distance gets farther away. But these two lines are of the same length, and this is the geometrical definition of a parabola. So what I want to do, though, is I want to consider extending these lines, but in the other direction. So we're thinking now kind of like those virtual lines we had before. Okay. So I'm to extend these lines in this direction by symmetry. And so what you see is if we now imagine that this is an array coming in like this, what it's going to do is it's going to reflect to the focus. All parallel lines will do that. All parallel lines coming into a parabolic reflector will reflect to the focus. And that's a special property of parabolas. Now, I'm not going to use the parabolic mirrors theoretically because your knowledge of parabolas is probably limited. They're harder to work with. And in reality, we more often encounter an approximation to a parabolic mirror, which is a spherical mirror. And so you can imagine that if I were to think of this region right here near the vertex, right, it does look a little bit like a circle, right? The circle will tend to kind of come around like this on it. So it's really only accurate within a very small region around the vertex right here. So we can approximate that as a circle. And so let's do that over here. So what I'm going to first do is construct a circle. Try to make a good circle, which I'm probably not going to be able to do. Let's say something like that. Okay, and then I'm going to put a center there. That looks like roughly a center. Right, so the distance from here to here would be the radius. I'm just going to draw a line through that. This line has a special name. We call it the optic axis, sometimes the primary axis. This looks terrible here. All right, so let me try and fix this circle up just a little bit. It should be more rounded down here. And the only part of this circle we're going to really use will be near the optic axis. The rays we'll be considering are called paraxial rays, so they're very close to the optic axis. And so what I'm going to do now is I'm going to erase the dotted line so that we don't get too confused. And so this is our spherical mirror. It's not great, but it's not bad. And it too will have a focus. And I'll describe in the a couple of lectures out the relationship between the focus and the center of the circle that we use to draw. This is called the radius of curvature, this radius. And that just defines the shape of the mirror. Right? So a larger radius of curvature, we have a flatter mirror. So what do reflections look like for this? Let me just make a note that there is this point called the focus. And it'll turn out that the focus, the distance from the vertex, which is also called the pole, and the point F, the focal point, is a distance F. We call it the focal length. The distance from the pole to the radius of curvature is the radius of the circle that we would have drawn. And the relationship between these two is that F is 1/2 of C. But now let's see how we can do ray optics on it. And I'm going to draw a little arrow here. That's our man standing some distance away. Actually, I might make him just a wee bit closer. So how do we construct rays? We need some rules for constructing these rays, right? We're going to base these on a couple of things. The law of reflection, which says the angle of incidence is equal to the angle of reflection. But we're also going to take advantage of this notion we got here. Parallel rays reflecting off a parabolic mirror will go through the focus. And I'm going to claim that the same thing will happen for a spherical mirror. And so what I can do to see what this is going to, how this is going to reflect is I can draw a parallel ray to the optic axis, like so. And I could, of course, try to figure out what the angle of incidence is by finding a normal at this point here, but that'd be awfully complicated. But I know that this should pass through the focus because it's just kind of the reverse of this, right? Light coming from the focus, right, wherever it hits on this parabolic reflector will leave parallel to the optic axis. That's why flashlights often have a parabolic reflector behind the light source. That way it comes out in kind of a beam. All I need to do to draw this is draw an incident ray that's parallel to the optic axis and make it reflect through the focus. Like that. Put a little arrow here. All right, so that's one ray I can draw. And I can reverse that, and I can say, well, you know what? If I were to pass through the focus, then I will reflect out parallel. So I can draw a line, or a ray, rather, through the focus. And the way it's going to reflect out will be parallel. Something like that. And finally, I can consider a ray that goes through the center of this. That's through the radius of curvature. If it goes through, remember, these are radial lines. So these lines are normal to the surface of the mirror. Unless I just imagine it's extended out. So it would reflect straight back. And so if I draw, well, I guess I should have not done that. Just need to fix my center a bit. If I send a ray through the center, then it will reflect back on itself because the angle of incidence is 0, because radial lines are normal to the surface of a circle. And there's one last ray that I can draw, and that would be one that goes to the pole. And one of the reasons that you might draw that is because this optic axis, that's the normal to the pole, to the mirror at that point. So we can easily do a law of reflection. So we see that we've got an angle about like so, which means that coming out we're going to need an angle of the same size. whoops, I lost it there at the end. Something like that. And notice that all of these are crossing at the same point right here. That is what we call the focal plane. Now remember, these are all rays coming from our head, so that means that our head is right here. Now you could do a similar analysis for your feet, presuming that you're standing on the optic axis, and you'd find that everything just reflects straight back, and your feet would be right here. And so what you get with a spherical mirror is a reflection, an image that's real. It's not virtual like with our flat mirrors where we appear to be behind it. If I were to hold a piece of paper right here and have someone stand right there, I would see an upside down image of them. That's a real image. And we'll talk more about that later, the details of that. But to draw this, you really only need two lines and you find where they intersect. So I could have picked the incident parallel ray, which is going to pass through the focus, and the one that goes through the center of the curvature. Or I could have picked one that goes to the pole. So it's up to you which one you use, or you could pick the one that goes through the focus and comes out parallel. That's the most common, I think, is to start with a parallel incident ray and then choose another incident ray which goes through the focus and see where they cross, because those are pretty easy to draw. So that is a spherical mirror and its reflection. And in problem sets, you can explore what happens as I move this object farther out, or as I move this object closer towards the center of curvature, or if I move it forward of that, all the way to the focus, what happens. And it'll be interesting to explore that, I think, because you'll find that you'll end up getting a virtual image behind the reflector. And that's why when these mirrors that you use to put on makeup or trim your mustache are spherical mirrors, and they magnify. If you look at it when you're close up to it, you get magnified. Actually, when you're right up to it, your head is the same size, but as you move it away towards the focus, your head gets bigger. Next, we'll talk about, just one note, these are concave spherical mirrors. Think of this as a little cave on this side, so if we're coming from the side with the cave, then it's a concave spherical mirror. Next, we're going to consider coming from the other side, which is a convex spherical mirror. So we're going to consider convex spherical mirrors. I can use the same mirror that I had before, but this time I'm going to come from this side. But the focus and the center of curvature, or the radius of curvature, will still be on the concave side. But I'm going to put my object over here, like so. Now, how do I apply these rules that I had before? Well, if I have a ray coming in parallel to the optic axis, like so. Since the focus is over here, what I can do to construct the reflected ray is consider the virtual ray going through the focus over here. So if you'll just simply lay out your ruler like so, there we go. I'm going to draw a dotted line for the virtual line over here, but the reflected ray will look like this. And probably another good option would be to reflect off the pole, because there we can just use the law of reflection to figure out what the reflected ray looks like. So if I draw from the head to the pole, like so, I want to get a comparable angle over on this side, reflecting out like this. That looks, of course, one way to do it would be to measure this height here, and that is going to be where we're going to go to, over here. There we go. So there's my reflected ray there. It would be interesting to extend this back as well. Oh, that was terrible, sorry. So I've got the extension of these two rays, and you'll notice that what you end up getting is a virtual image again, just like with the flat reflectors. Except that, look how small the height of this guy is compared to this. It would be bigger if I moved it closer. But if you've ever been in a car and looked out the rearview mirror and you see it say something like objects in mirror are closer than they appear, and this is why. Because your rearview mirror, or not, what do they call them? The side mirrors on a car are actually convex mirrors, convex spherical mirrors. And they're used because we can reverse this and think of rays coming in from this direction. It will follow exactly the same path. And this allows me to see a much wider field of view. You see them at parking garages a lot when you pull out, there'll be a big spherical mirror that allows you to see all the traffic coming from around the corner, where a flat mirror would not allow you to see those. So that's the use of that. The image is virtual, which means it's behind the mirror, or appears to be behind the mirror. Yeah, and that's it. That's all I'm going to say about convex spherical mirrors. Next, we'll derive or show the relationship between the focus and the radius of curvature.